So this is section 13.8 part B. So I'm separating this from 13.8A because together they're very long. So I'm going to basically treat them as two separate chapters, or separate sections if you like. This is on absolute max and min in very specific situations. So just to explain what we're looking for here, let me just do a reminder of what we did in Calc 1. A couple of thoughts from Calc 1, and then we'll sort of mention the same things for Calc 3, and then talk about the method. So in Calc 1, we looked for max and mins of functions, but we couldn't do it under all circumstances, right? So in Calc 1, so we could find min and max, max and min of f of x, but only in certain situations. And basically, only in one situation, like one fair restriction. So here's an example of when we couldn't necessarily. Is if we just had a function and no restrictions on it. In other words, a function like, say, this. So this function right here, there's no restrictions. There's no restrictions basically on the interval, like on the x range, right? Since there's no restrictions on x, here this function, this f has no min or max. Or another example of no might be when you've got something like an asymptote. So you might have something like this. Here there's this f has no max. So what we did in Calc 1 is we restricted ourselves. So in Calc 1, we restricted to a continuous function on a closed interval. Okay, AB. So there's a theorem in calculus that states that if you have a continuous function on a closed interval, that it has to have a max or a min. That's totally not continuous. That is the wonkiest function ever. That's totally not a function, actually, but anyway, here we go. So like this, it's continuous, it's nice, it goes from A to B, stops at A and B, that's great. Here we have a minimum, we have a maximum, we can label those, and it's guaranteed to have this because it's continuous on a closed interval. If it were not continuous, like the second example, if it were not on a closed interval, like the first example, it wouldn't necessarily have a max or min. It might, but wouldn't necessarily. So by sticking with this restriction, we guarantee that it does. So the question then becomes, so the goal in 13.8B is to do the same with a function specifically of two variables. So that's f of xy. So the question then becomes to think about is how do we restrict the x and the y's, right? In Calc 1 we said the x had to be an AB, right? So in Calc 1 we had to have x in an interval AB. What do we require? For Calc 3, for this f of xy, or just really for this xy. So what we'll do is we'll talk briefly about what the requirements are, and then we'll talk about how we did it, how we approach it. So let me clear the screen and start on the requirements for Calc 3. So let's say this. Let's just call this what guarantees a max or min, a max and min, let's say, because we're looking for both, for f of xy. So the answer is this. This is where we'll focus. If f of xy is continuous, and we focus on x comma y in what's called a closed and bounded region. So let me sort of, without giving a formal definition of closed and bounded, let me sort of give an informal definition. So closed means it has to include its edge. So must include edge. I'll draw some pictures in a second so that it's clear what's going on here. And bounded means it doesn't stretch to infinity. So let me draw some examples of things that are not these things. That'll help us see. So this next R is not closed. So if I have a region, I'm going to draw this in, say, red, and I don't include the edge. So think of like, so I'm going to fill it in. This would be something like x squared plus y squared is less than 9. Right? Doesn't include the circle. This is an example of a region which is not closed. So this next R is not bounded. So something that maybe goes forever and ever and ever, like to the left and right. This would be something like y is between, say, 3 and negative 3. So this guy, this next one is closed but not bounded. The one before that is bounded but not closed. So what we're going to do is we'll stick with regions like the following. I'll draw 2. So we'll just require that you draw like a finite region that has to contain its edge. So for example, something like this would be good. Something like oval would be good. Things like this. Things that don't have any of this weird behavior that came up in the first 2 examples. So that's the situation. I.e., just to clarify, we'll have f of xy continuous and defined on a region like this. Let's say on a R like these. And we'll find the max and min. So then the next question is how? So again, just a brief reminder of what did we do in Calc 1. We did the following, right? We had a function, we had an interval. This is what we did. Once we remember what we did, it'll help us understand why we're doing what we're doing in Calc 3, is we found the critical points in the interval. We ignored outside of the interval, and we plug those into F. We did 2 things really, and second is we plugged the endpoints into F. And from amongst all those, we choose the max and min. So the reason for checking the endpoints is that the max and the min may occur at an endpoint, and that may not be a critical point. So the endpoints become special. So you check the critical points because the max and min could happen there. You check the endpoints because the max and min could happen there. And out of all of those things, you pick the biggest and the smallest. That's what you do. So what's the analogy? Like, what does a critical point mean for a function of two variables? And what is the analogy for finding the endpoints? So what does this mean? What do we do in, let's say, Calc 3? So let me clear the screen, and then I'll give a general method, and then we'll do a couple of examples. So we'll say method finding max and min of f of xy with x and y restricted to a closed and bounded region. So step 1. So what I'm going to do is I'm going to find the critical points. So I really need a definition of this just to be clear. So a critical point for f of xy is a point where both f sub x and f sub y are 0, or f sub x or f sub y do not exist. Now mostly we'll be looking at the cases when there's 0, so the place to focus your attention is this. Tend to stay away from the ones where the derivatives don't exist. So what we do here is we find the critical points inside the region. We plug those into F. And then step 2. What we do here is we find the max and min of F on the edge of the region. Now, how we do this is a little confusing the first couple of times, so I'm going to give it just sort of a general rule, and we'll work it out with some examples. So we do this basically by using the equation of the edge to rewrite f as a function of one variable, and examining that. This is a very general statement here. It's sort of lacking of specifics really, but we need to do some examples to see. And step 3, out of all the max and mins, we choose the biggest and the smallest. Out of, let's say, all the values in steps 1 and 2, choose the max and min. So let me start with a really simple example. Just so we can see these side by side. We'll find the max and min of f of xy equals 2x squared minus 3y squared on x squared plus y squared is less or equal to 4. So just so we really understand what's going on here, x squared plus y squared is less than or equal to 4 is a circle of radius 4. It's filled in. This is the restriction. This is our R. And basically what we're saying here is that x and y can be anywhere in that region, and then how big and how small can f be if you're allowed to be anywhere in that region. So the first thing we do is find the critical points. So we take f sub x, we get 4x, we set that equal to 0. We take f sub y, we get negative 6y, we set that equal to 0. This is a ridiculously nice system that gives us a single critical point, which is 0, 0, because x and y are both 0. So we take that, we plug that into f. We get 0, and we just note that point. Like, I'm going to put a green box around it. We just be like, hey, that's what's going on at the critical point. And then what we do, we just put that aside. That's step 1. And then we look at the edge. So the edge is where x squared plus y squared equals 4. Right? Because less than 4 is the inside of the disk, and equals 4 is the edge of the disk. So what we do is, I'm going to take that, I'm going to use it to rewrite f. So from here, take a look. I can say that y squared is 4 minus x squared. That's if I'm on the edge. So then f, which was 2x squared minus 3y squared, I can rewrite that as 2x squared minus 3 times this. So f is equal to, so if I solve this, I get 2x squared plus 3x squared is 5x squared minus 12. And this is on the edge. Now, notice if I'm on the edge, x is between 2 and negative 2. That's because up here on the picture, this is a circle. Right? So we could say, hey, it's a circle of radius 2. So also here, on the edge, x is between negative 2 and 2. So then what I'm going to do is I'm just going to do this intuitively. I'm not going to do anything too technical. I'm going to say, hey, look, if f is 5x squared minus 12, and if x is between negative 2 and 2, what's the biggest this could be? Right? So the maximum will occur when x is plus or minus 2. Then I get 5 times plus or minus 2 squared minus 14. So this happens at x equals plus or minus 2. All right, so all I'm doing is I'm thinking about these x's and what I get when I plug them into f. Nothing technical. So plus or minus 2 gets me the most. So when x is plus or minus 2, f is 5 times 4 minus 12. So this is 8. And the min, this occurs when x is 0. So that's at x equals 0. And when x is 0, that gives me negative 12. And so I take those values and I put a green box around them. Otherwise, I'm like, okay. So this is what we figured out so far. We figured out that basically inside the circle, I can get 0 as sort of like a relative max or min, if you like. But you don't need to think about it that way. And then on the edge, I can have a max of 8 and a min of 12. So we look at all of those together. Right? So amongst all of them, all of those 3 values in this case, the max is 8, the min is negative 12, and that is it. Right, so it's kind of like the Calc 1 version, but the definition of the analogy for the endpoints now becomes the edge. And so to deal with the edge, we need to sort of figure out what to do with the equation of the edge to get a solution. So let me do another example that's a little more complicated, and you'll see why when we do it. So I'm going to clear the screen off so we can have space to do the second example, but the spirit of the problem is going to be the same. We're going to find the critical points, test those, that if there's just one, and then look at the edge and see what we can say. So what we'll do is we'll say this, find the max and the min of f of xy equals x squared plus y squared. Actually, let me do something that's slightly easier. Let me just make it, say x plus 3y, where x and y are restricted to the triangle with corners, say 6, 0, 0, 3, and 6, 3. So a picture of this, just so we know what we're looking at here, in this case, is we're saying that the point is restricted to the triangle with a corner here, at 3, over here at 6, and then at 6, 3 here. So this is filled in, is the intent in this problem. So that's our region now. Notice that the edge is sort of comprised of 3 pieces. It's worth noting that right now, but we don't need to worry about it exactly this second, right? So the spirit of the problem is the same. First, we find the critical points. So we take f sub x, that's 1. We take f sub y, that's 3. We set them equal to 0, which seems a little absurd, because what this says is there are no critical points. Right? That's fine, not a problem. No critical points, done. Right? So then we check the edge. Now the edge is in 3 pieces. So what I'm going to do is I'm going to go back and label them, because I need to do this 3 times, and no particular step is difficult, but in fact they're all pretty quick, but we need to pay attention. So let me call this edge, say, A, I'll call this B, call this C. We'll do them independently. So let's look at them in order, right? So if I focus on A, y is equal to 3. And x is between 0 and 6. So look at f, right? F is x plus 3y. But y is 3, so this is x plus 9. So now what we do is we look at this particular f. This is on this particular edge. This is on A specifically. So if f is x plus 9 and x is between 0 and 6, the minimum is at x equals 0, at which f will be 0 plus 9, which is 9. And the max, this will be at x equals 6, will be 6 plus 9, will be f will be 15. So what I do is I'm going to put some boxes around those, just so I keep them in mind. Then we move on to the next piece of edge. So there we go, on B. So on B, we see that x is 6. And y is between 0 and 3. So then we go, well, what's f? F is x plus 3y. X is 6, so this is 6 plus 3y. Again, this is on B, just to really reiterate. So we say, what's the minimum? Well, the minimum will occur when y is as small as possible, when y is 0. And at that point, f will be 6. And the maximum will occur at y equals 3. When y is 3, I get 12. So, put some boxes around those. Mistake there. When y is 3, hold on. Yeah, when y is 3, sorry, I get 6 plus 9, which is 15. Let me fix that. Sorry about that. Oops, make that black, so the colors all match. So we put boxes around those, go with that. And then we look at C. C is a bit trickier, because on C, neither x nor y is a constant. But on C, we know that's a line that has intercept at 3 and slope negative 1/2. So on C, y is 3 minus 1/2 x. And x is between 0 and 6. So what's f? F is x plus 3y. But y is 3 minus 1/2 x. So this is x minus 3/2 x. This is minus 1/2 x plus 9. Again, this is on C specifically, where the minimum is. The minimum is at, in this case, x equals 0. This will be f will be 9. And the maximum will be at x equals 6. This will be negative 3 plus 9, f is 6. So same big deal. We take those, put boxes around them just to reference them, and then we look at all of those, 6 values in this case. So amongst all of those, right, the min is 6, the max is 15. That's the final answer. So let me do just one more that's sort of a combination, a little more confusing than these two. So for a third example, this will actually be fairly challenging, but I think it's an interesting one anyway. So let's find the max and the min of f of xy. It's challenging because the edge bit gets to be a bit sneaky. Equals, say, x plus y squared with, let's say, x squared plus y squared less or equal to 4, but x greater than or equal to 0 and y greater than or equal to 0. So in other words, graphically what's going on is this is where we are restricted. It's a quarter circle. It's a filled-in quarter circle in the first quadrant. So positive x and y, and the function is x plus y squared. So we proceed as usual, find the critical points if they exist. It's not uncommon for these problems, for sort of fairly simple ones that we're doing, that the critical points, maybe there's one of them or none of them. So like in this case, again, just like the previous example, take my partials, set them equal to 0, but the first one rejects it, so there's no critical points. So that's out the window. So take a look at the edge. So again, like before, like the previous example, in fact, the edge is in 3 pieces. So we've got, we'll do the easy ones first. That's A, that's B, tricky one will be C. We'll see why. So when we do A, say well for on A, now again, keep in mind this circle is radius 2, this goes to 2 and 2. So for on A, then x equals 0, and y is between -2 and 2. So f, which is x plus y squared, which is 0 plus y squared, or y squared. Again, this is on A, just to reiterate, the minimum will occur when y is 0. Here, f will be 0. The maximum will be at y equals 2, and f will be 4. So box those up, keep those in mind. And then we'll look at part B. We'll look at edge piece B. So at edge piece B, y is 0, and x is between 0 and 2. So f, which is x plus y squared, y is 0, this is just x. Again, on B specifically, the minimum will occur at x equals 0, which will be f equals 0, and the maximum will be at x equals 2, which will be f equals 2. So likewise, box those up, those are the values. And then we go to this last edge piece. This is trickier, right? Because what happens is we go, okay, well look, this is where x squared plus y squared equals 4. So this is a bit like the first problem that we did. The thing that makes it tricky is when we go back to f. So here, what we're going to do is I'm going to solve for y squared, but like before, because f has a y squared in it. So f, which is x plus y squared, this becomes x plus 4 minus x squared. And this is, here, we have x between 0 and 2. If we see the picture, right? So this isn't as obvious what the max and the min is, right? But this is really just a Calc 1 problem, right? We can rewrite this and say like, hey, this is a Calc 1 problem. In fact, this is a problem that's kind of like what we started the discussion with, right? We have a function, it's continuous on a closed interval, 0 to 2, and we want to know how big and how small it is, right? Now, this isn't particularly terrible. We can do it the same way. We can find the derivative, right? So there are two ways you can do this, actually. Let's mention this. You can observe that it's a parabola, that it opens down. And so you could find the maximum maybe at the top, and they could check the endpoints. But let's be really Calc 1-y about it. Let's find the critical points. And again, this is in a Calc 1 sense now, right? This is all like Calc 1 again. So f prime, I'm writing f prime, which is a little irresponsible, but it is a function of one variable now. So we have negative 2x plus 1, set that equal to 0. Get x is 1/2. And so at that point, if I plug in 1/2, we get negative 1/2. Let me make that tidy. Negative parentheses 1/2 squared plus 1/2 plus 4. This will be a negative 1/4 plus 1/2 plus 4. This is 5 1/4. Or if you prefer, 21/4. So I'm going to, eventually I'll put a box around that, but we'll come back to that. Then I test the endpoints. So we check this f at 0, we get 4. Take this f at 2, we get negative 2 squared plus 2 plus 4. This is negative 4 plus 2 plus 4 is 2. So on this edge, we've got all these sort of interesting places of values. So if you look at all of these, so amongst all, the min, if we look about them all, we get a minimum of 0. We have a maximum of 21/4. That's our final answer. Now, so this one's a bit confusing, especially because of this middle step of dealing with this this part C, right? Like all of, let me just label it so it's clear. All of this was dealing with C. So be aware of that. But otherwise, the spirit of the problem is the same. We're saying like, hey, look, you know, what's going on the edges? The edge is in 3 pieces. In this case, one of the pieces is particularly ugly. I like doing this problem, though, and I'll tell you why, is it's a common belief sometimes, and it's very frequently true that the max and min occur at corners of points. And so it's very, you know, it's a common mistake among students to just try the corners. So students on this problem might try 0, 0, 2, 0, and 0, 2, and forget everything else. And so this is an example, right? If you look at where this happens, right? This happens at x equals 1/2. Right? On our picture, just to reference this, in case you're interested, if you go back and you look, x equals 1/2 is right about there, and we're on the curved edge. So this is where the maximum is occurring. So that's a little tricky, right? It's not obvious at all. It's not a corner. It's sneaky. So it's a good problem to do because you get an unusual answer. But and it's not too bad. If you have time to calculate it, you can sort of go through and hash out why it's working. So anyway, that's the end of 13.8B.